Hey guys, in this video we're going to talk about Chapter 13, Section 4, the cross product. So in the last video we talked about the dot product. We talked about creating a product between two vectors, and the product in question was a scalar, right? It was just a number. Now here we're going to take another product of vectors, so we're going to define it differently than the dot product, but the resulting product is going to be an actual vector this time, not a scalar. So the cross product is different from the dot product in that way. And let's go ahead and explore what the cross product means geometrically. Before that, we need to remind ourselves what a parallelogram is. So you probably haven't seen a parallelogram since high school geometry. I don't know, maybe you've seen it in trig, or maybe even algebra 2. I'm not sure. But nevertheless, let's talk about it again. So parallelograms are basically shapes that have four sides, and the opposite sides are parallel to one another. Now, in geometry, you talked about a formula for the area of a parallelogram, and that formula was area is equal to the base of the parallelogram times the height of the parallelogram. And we can see here that our base is just the bottom, and our height is the length from the very top of the parallelogram from the very bottom, perpendicular with the base, okay? So that was our definition from high school geometry. Now let's talk about the definition of the area of a parallelogram in terms of vectors, okay? So suppose a parallelogram is formed by the vectors v and w with an angle of theta between them. So if that's the case, maybe we have the magnitude of w right here. So here's the start of our vector. There's our vector w, or the magnitude of w rather. And then we have v right here, so this is going to be the magnitude of v. It's that length of this purple vector right here. Okay, and then we have some height associated with the parallelogram, so from the top to the bottom. So the question is, how can we get the area formula in terms of v, w, and theta? Well, we know that the base of this parallelogram is going to be the magnitude of v. So let me just actually rewrite this. So we have the area of the parallelogram is just base times height. But I want everything in terms of v, w, and theta, okay? So the base, we can definitely write that in terms of v. The base is simply the magnitude of v. It's just the length of v. Okay, so that's the base. Now the height, how can I turn the height into v's, w's, and thetas? Well, observe the following. So if we have this guy right here, we have this height right here, then this guy right here is the magnitude of w, right? And so this makes a right angle right here, and this is going to be theta right there. So how can we talk about h in terms of theta? Well, we can set up a trigonometric equation. We can say, well, the sine of theta is equal to opposite, which is h, over hypotenuse, which is the magnitude of w. Isolating h, multiplying both sides by magnitude of w, we get sine of theta times magnitude of w is equal to h. Okay, so that's our height. So instead of the height, we can put sine of theta times the magnitude, and maybe I'll just leave the times out of here just so we don't get confused with the dot product. Magnitude of w. Alright, so the area formula becomes this right here. Okay? And if we want the sine of theta to come at the end, we can simply use the fact that multiplication commutes, and we have magnitude of v times magnitude of w times the sine of theta. And so that is going to be our area right here. Okay, so we define the cross product of two vectors, v and w, written v cross w, to be a vector perpendicular to both vectors v and w. The magnitude of this vector is the area of the parallelogram formed by the vectors, and the direction of this vector is given by the normal vector n to the plane defined by v and w. Okay, so here I have a picture of pretty much all of this, what is set up here. Instead of v and w though, I have a and b, okay? And so we have our vectors a and b. B is in red, a is in blue. We have the angle between them, theta. And this picture is illustrating the, first of all, it's illustrating the cross product right here. This is a cross b, this vector right here, perpendicular to both a and b. As you can see, if you look at it from the front, here's the perpendicular to a, and if you look at it from the side, here's the perpendicular to b. So that vector is perpendicular to both of those guys, and the magnitude of that yellow vector up there is going to be the area, of this parallelogram formed by vector a and b. Okay, so the right-hand rule basically tells us which direction your normal vector is pointing. And so this is just how you do it. You literally use your right hand, and you place vector A and B so that their tails coincide, and then you curl your fingers of your right hand through the smaller of the two angles from A to B. Your thumb is going to point in the direction of the normal vector to A and B. So this is, kind of the diagram of how you do it. So if you have one vector A, your index finger is going to point in the direction of A, and then if you have another vector B, your middle finger is going to point in that direction. And then when you go from A to B, when you curl your fingers in the direction of this angle right here, you're going to see that your thumb is pointing straight up, and so your normal vector, the cross product, is going to point straight up. So let's talk about the geometric definition of the cross product. If v and w are not parallel, then the cross product v cross w is equal to the area of the parallelogram formed by v and w times a normal vector. So we have the magnitude of v times the magnitude of w times sine theta, which we already saw a few slides ago was the area of that parallelogram, times a normal vector. Theta is going to vary between 0 and pi. It's going to be the angle between v and w. And n is going to be a unit vector, okay, so magnitude 1, perpendicular to v and w, pointing in the direction given by the right-hand rule. And an important little tidbit is if v and w are parallel, then the cross product is equal to 0. And why is that? Well, because think about it, if v and w are parallel, then they're laying on the same line, right? They're pointing in the same direction, and so they can't form a parallelogram. And hence the area of the parallelogram would be 0, right? Because there is none. And so the whole cross product would be 0 as well. Okay. So let's do an example using our geometric definition to figure out what the cross product of I plus j and I minus j is. Okay. So let's go ahead and do a little sketch of our vectors here in the xy plane. And we can see that we don't have a k component, which means that we're just working on the xy plane, which is nice. That makes our lives easier a lot of the times. And so the first vector we have is we have 1i plus 1j. So if I go 1 out in the x direction and 1 out in the y direction, my vector looks something like this. All right, so this is the magnitude. This length is the magnitude of I plus j. All right. And then we're going to cross it with I minus j. Okay, so we go 1 out in the I direction, and then we go minus 1 in the j direction. So -1 is going to look something like that. Okay, and this is going to be the magnitude, maybe I'll write it a little bit closer, the magnitude of I minus j. Okay, so that's what that length represents there. And we want to figure out what the angle between them is, right? Because we're starting from here, since this is the first, since the yellow vector is the first vector that comes in my cross product, right? It's the first one there. And then we're going here, so we want to figure out what this angle is. And so that is going to allow us to get our cross product, right? Because V cross W is going to be equal to the magnitude of V times the magnitude of W times the sine of theta. I should really not put a dot there, just to not get it confused with the dot product. And times normal vector. So something normal to both V and W. Okay, so how do we figure out what that angle is? Well, if we kind of draw our triangles off to the side, so we have this triangle where the magnitude I plus the magnitude j is going to be on our hypotenuse, and what else do we need? Well, we know that you know, I'm talking about this triangle right here. We know that the base is 1, right? Because we go out 1 in the x direction, and we know the height is also 1 because we go out 1 in the j direction. So this triangle is 1, 1. And the magnitude of I plus j, remember how we computed that? We just took the square root of the squares of the coefficients. So that was just root 2. So this guy is simply root 2. And you should recognize this, hopefully, from your unit circle, right? Here's theta. And so the cosine of theta, or the sine of theta if you like, it's going to be 1 over root 2. And if we do the inverse of this, you know, you can do it in the calculator, or you can just think back to your unit circle, which angle has a cosine of 1 over root 2, and that angle has to be 45 degrees. Right, so this guy, let me write it right here. This guy is 45 degrees. So this is 45 degrees right here, this little piece. And then for the other piece, I mean, you can do the same thing, right? We have a triangle right here. This is my green triangle. The base is the x component. That's 1. The height is -1. Let me see something. Let's see. I don't know why that came up. Actually, let's go ahead and do that. Okay. So we have -1, 1, and then the magnitude, again, of I minus j is just the square root of 1 squared plus 1 squared, which is the square root of 2. So again, this theta, the absolute value of theta is 45 degrees. So this piece right here is also 45 degrees. And so because we're starting here and ending here, right, it's 45 plus 45, but we're going in the clockwise direction, right, because this is our starting vector crossed with our second vector. So since we're going in the clockwise direction, this is going to be -90 degrees in total, okay? So the angle between those vectors is -90 degrees. So we already figured out everything. V cross W, the magnitude of V we just saw was root 2. Magnitude of W was, again, root 2. So we have root 2 times root 2 times sine of -90 degrees times a vector that is perpendicular to both v and w. Well, guys, v and w both lie on the xy plane, right? There's no z component, there's no k. So because those two lie on the xy plane, a normal vector to both of those is going to be k, right? Just the vector. So k is the vector 0, 0, 1, and is perpendicular to both I plus j and I minus j. Okay, so since that's the case, we can say that our normal vector n is k, and our answer here, v cross w, well, square root of 2 times root 2 is just 2, sine of 90 is negative 1, and our normal vector that we found is k. And so our answer here is negative 2k. That is the cross product of v and w. So that is a vector that is both perpendicular to v and perpendicular to w. We also have an algebraic definition for the cross product, and this is the formula right here. It is kind of long and cumbersome, but that's it. And we're just assuming that our vector v has coefficients v1, v2, and v3 in the x, y, z positions respectively, and w is w1i plus w2j plus w3k. So this is the formula that we're going to be using the most, so let's go ahead and use an application of it here. Alright, so we want to find the cross product of v and w, and check that the cross product is perpendicular to both v and w. So because my formula has all of these coefficients, I'm going to start by writing those out first. So v1, v2, and v3, and maybe I'll write my formula out at the bottom just so we have it here. Okay, so there is our formula. Okay, so in our case, v1, the coefficient of I is 2, v2 is 1, coefficient of j, and v3 is negative 2. Then for w1, the coefficient of I is 3, w2 is 0, we don't have a j, and w3 is 1. Okay, so now we are going to apply the formula here, and I know, it's messy, but it'll look nice at the end. So the first thing is v2 times w3. So we have 1 times 1 minus v3, negative 2 times w2, which is 0, I, plus v3 is negative 2 times w1, 3, minus v1 is 2, w3 is 1, j, plus, and finally w1 is 2, w2 is 0, minus v2 times w1, and that's times k. Okay, and now we just need to simplify this guy. So up here we have 1 minus 0 is 1, so that's 1i. Okay, over here, negative 6 minus 2 is negative 8. Negative 8j. 0 minus 3 is negative 3k. So this is our cross product, and again, This guy is supposed to be perpendicular to both v and w. So let's check that. Now remember, from last time, two vectors are perpendicular to each other if and only if their dot product is 0. So we need to use the dot product this time to check that they're perpendicular. So the first question we're saying check is v, which was 2i plus j minus 2k. Is that perpendicular to the vector we found? And so we just use the dot product, right? So is dot product 0? Well, we know how to do the dot product. We multiply the coefficients, the corresponding coefficients, and we add them all up. So 2 times 1 plus 1 times negative 8 plus negative 2 times negative 3. And so that is going to give us negative 6 plus 6 is indeed equal to 0. So yes, they are perpendicular. Now let's check the other vector. So now we check, is the other vector 3i plus k perpendicular to the vector we found? Well, again, we take the dot product. So we are doing 3 times 1 corresponding coefficients plus no j's here, so 0 times negative 8 plus no j's there, I meant, plus 1k times negative 3. And so this is going to, again, give us 3 minus 3 is 0. So yes, both of those vectors are perpendicular to the one we found, which we expected, because that is what the cross product is supposed to give us. Okay, so for any vector v, find v cross v. Okay, so you could use the algebraic definition if you wanted to, and give some components for v and figure out what the cross product is that way. I think it's a little bit more useful to use the geometric definition in this case. So the geometric definition says that v cross v is going to equal the magnitude of v times the magnitude of v times the sine of the angle between them times a normal unit vector to both of those vectors. In this case, it's the same vector v. So the key observation here is that we know what the angle between a single vector is. It's 0, right? Because if we have a vector v and then we have another vector v, the same exact vector, it's going to be laying on top of each other, right? Or it's going to be laying on top of itself, excuse me. Or it can be shifted to make it lay on top of itself, right? It's in the same direction. And so the angle between a vector and itself is going to be 0, right? So sine of theta becomes sine of 0. And then we have, of course, everything else that carries down. Okay, now the sine of 0 is 0, so this whole thing goes to 0. Okay, so the lesson here is that a vector crossed with itself is just 0. That is all that is. Okay, so anytime you see a vector cross with itself, know that it's going to be equal to 0. Okay, let's do an example here. Find a non-zero vector perpendicular to the two vectors v and w. All right, so when we're trying to find a vector perpendicular to both vectors, we're going to do the cross product. Okay, so we want to do v cross w. And so I'm going to use my algebraic definition that I'm going to write again down here so you guys can follow along. Okay, so there is our definition of the cross product. So let's go ahead and compute this guy. All right, first of all, let me list out my coefficients. V1 is 3, V2 is 2, and V3 is -1. For W, we have W1 is 6, W2 is -2, and W3 is 5. So using the formula below, we have W2 times W3, so 2 times 5 minus V3 times W2 I plus V3 -1 times W1 minus V1 times W3 J plus V1 3 W2 -2 minus 2 times 6. Okay, so let's go ahead and clean that up. So we have 10 and 2. Wait, did I do something wrong here? 10 and 2. No, that's 10 minus 2, sorry. That should give us 8. And then we have -6 minus 15. -21j. -6 minus 12 is a -18k. Okay, so this right here is a non-zero vector that is both perpendicular to v and also perpendicular to w. So recall that if we're given a normal vector to a plane and a point on the plane, we can describe the plane by the following equation that's boxed above. So let's do an example where we're given 3 points on the plane and we can use the cross product to figure out the normal vector to that plane. Okay, so we're given 3 points on the plane, and I'm just going to sketch the plane out as well as the points, not really being super careful about the accuracy of where the points are with respect to each other. So we have P is 1, 3, 0. That's P. And then we have R. Again, I'm not drawing this super accurately. But we have R is 3, 6, 2. And then Q is maybe over here. And that's 3, 4, -3. Okay, and we want to figure out what the equation of this plane is. So the first thing we need to do is we need to figure out some vectors on this plane, some displacement vectors. Then once we do that, to figure out what the normal vector of the plane is, which we need for the equation, we're going to take the cross product of two displacement vectors, okay? So let's go ahead and figure out some displacement vectors. I'm going to look at the displacement vector PQ, so P to Q. And then I'm also going to look at PR. So this is another displacement vector starting at P, ending at R. And so once I figure out what those vectors are, then what I'm going to do is I'm going to find the cross product of those vectors. And what that's going to give me is it's going to give me the normal vector, because it's going to be perpendicular to this vector PQ right here, and it's also going to be perpendicular to any other displacement vector on this plane. Okay, so let's go ahead and figure this out. Alright, so first of all, let's figure out what PQ is, the vector PQ. So that's our displacement vector. We're terminating at Q, so we're going to take the difference in the x's. So I have 3 minus 1, difference in the x's, I, plus the difference in the j's, so then we have 4 minus 3, j, plus the difference in the z components, the k's, and we have negative 3 minus 0, k. Okay, so then if we simplify this, we get our displacement vector is equal to 2i plus 1j minus 3k. Okay, so that is PQ. And let's go ahead and figure out what PR is as well. So PR, okay, so we're terminating at R, so we're taking the difference in the x's, starting with R. We have 3 minus 1, I, plus 6 minus 3, j, plus 2 minus 0, k. Okay, and then we can simplify this out to give us PR is equal to 2i plus 3j plus 2k. Okay, so there's PR, and here is a vector PQ. Okay? So again, if we take the cross product of PQ and PR, these two displacement vectors on our plane here, we're going to get a normal vector. So we're going to get a vector that's perpendicular to both PQ, PR, and any other displacement vector on our plane. Okay, so let's figure out what PQ cross PR is. Okay. So again, the cross product, I mean, what you can do if you want to, you can say, okay, well, PQ is going to be our V, so V1. Maybe I'll erase some of this just to make it a little bit neater. So we're taking the cross products. We need our V1s, V2s, V3s, etc. So we have V1, V2, V3. So V1 is 2, right? V2 is 1, coefficient of j, and V3 is negative 3. And then for our W, so our other vector is PR. So our W1 is 2, W2 is 3, and W3 is 2. Okay, so then let's just go ahead and apply the cross product formula here. So again, we're acting like this is our V and this is our W. So we have V1, I'm sorry, not V1, we have V2, which is 1, times W3, 2, minus V3 times W2, it's going to be I, plus V3 W1 minus V1 W3 plus V1 W2 minus V2 W1. Okay, so cleaning this up a little bit, we have, let's see, 2 minus, is that, let's see, let me just double check that. Yeah, that's a 3. Sorry, that's not very clear there. But okay, so we have 2 minus a negative 9, so that's going to give us 11. So we have 11i. And then negative 6 minus 4 is negative 10j. 6 minus 2 is positive 4k. Okay? So this is our normal vector, right? Because it's going to be perpendicular to any of the displacement vectors on the plane, right? We found that by finding the cross product of two displacement vectors. So that's our normal vector, and so we have A is equal to 11, B is equal to negative 10, and C is equal to 4. And now we can figure out what the equation of the plane is, because in the very beginning we were given 3 points that are on the plane. So use any of those points. I'm going to use P as x naught, y naught, z naught. So x naught is 1, y naught is 3, and z naught is 0. Okay? So again, we're just using this formula right here for the equation of the plane. So we have A times x minus x naught plus B, which is just going to be a minus 10 times y minus y naught, plus C times z minus 0, which is just z, equals 0. And so, we could clean it up a little bit if we wanted to. Distribute that 11 in there and get 11x minus 11. Distribute the negative 10. Negative 10y plus 30 plus 4z is equal to 0. And then, let's see, this is going to be 11x minus 10y plus 4z plus 19 equals 0. So that is going to be the equation of our plane. And again, this is the normal vector to the plane. This is the vector that is perpendicular to any other displacement vectors on the plane. So we want to find a vector parallel to the line of intersection of the two planes, 3x minus 5y plus 2z equals 8, and 10x plus 4y minus 6z equals 20. Alright, so this is just a sketch of two planes, and we're just to get the point across, we're going to pretend that they're these planes in question. So we have this yellow plane right here. Again, this isn't drawn to scale, just to get the point across. Here's our plane, and then we have this other plane that's intersecting it in green. And when they intersect each other, they intersect each other in a line. So let's have the line of intersection right here. This purple line right here, that's the line of intersection. And so we want to figure out a vector parallel to this line of intersection of these two planes. Okay, so the idea here is that if we find a normal vector to both of these planes, when we take the cross product, we're going to get something that is parallel to the line of intersection. So let me see if I can draw this for you so that you can see what I'm talking about here. So, the yellow plane, Q, as it's labeled here, is going to have a normal vector that's sticking straight up, right, at a 90-degree angle. So let's call that normal vector N1. Okay. And then the other plane, P, is going to have a normal vector that is coming straight out of it. So P, let's actually do this in orange. So P is going to have a vector that makes a 90-degree angle with the plane there. So we could call this one N2. And so the idea is if we cross those guys, we're going to get a vector that is perpendicular to both of those and hence parallel to the line of intersection. So we're going to have something that looks like this. We're going to have our 90-degree angle here and our 90-degree angle down here. So we're trying to find, and then maybe that's our parallel vector. Let's do it in blue. Okay, so we're trying to find that parallel vector that that makes a 90-degree angle with n1 and n2. So they're perpendicular, and that's going to be a scalar multiple of the line of intersection. So that's the idea. That's what we're doing here. We're going to cross n1, cross n2. That's going to give us a vector that is perpendicular to both n1 and n2, and hence it's going to be parallel to the line of intersection. Okay, so let's go ahead and do that. First thing for n1, so remember our normal vectors are of the form ai plus bj plus ck and so just based on what we have here for our yellow plane, we have A is 3, B is -5, and C is 2. So N1 is just going to be, and actually these little arrows are not in the best place. They should be over I, J, and K. Okay, so N1, we're going to have 3I minus 5J plus 2K. So that's our equation for N1. Now for N2, same idea. This time we are looking at this plane, right, because it's normal to this green plane. And so for N2, we have 10I plus 4J minus 6K. Okay, so now the idea is that we take the cross product of these. And again, the cross product is just spitting out a vector that is perpendicular to both of those guys. And so it's going to be parallel to the line of intersection. So let's go ahead and cross them. So we have N1 cross N2. And again, you know, if it helps you out, you can label N1 as your V. So V1 is 3, V2 is -5, and V3 is 2. And then for N2, that's acting like our W in the formula. So W1 is 10, W2 is 4, and W3 is -6. Okay, so applying the formula, we get -5 times -6 minus 2 times 4I plus 2 times 10 minus 3 times -6 J plus 3 times 4 minus -5 times 10 K. Okay, so simplifying that all out, we get 22I plus 38J plus 62K. So this vector is perpendicular to both N1 and N2, and it's parallel to the line of intersection on the intersection of the two planes P and Q, or the yellow plane and the green plane.